Right now, two teams of physicists are measuring how fast the universe is expanding and getting two completely different answers. The disagreement has crossed 5 sigma, the gold standard of statistical proof. At this level of certainty, the odds of a fluke are 1 in 3.5 million. Something is fundamentally wrong with our model of reality, and no one knows what. This crisis is a symptom of a cosmic reckoning. For nearly a century, we built a grand cage of mathematics to contain the behavior of the universe. We call this cage the Standard Model of Cosmology, or Lambda CDM. Lambda represents the dark energy pushing space apart, while CDM stands for the cold, dark matter holding galaxies together. This model was a triumph, a perfect harmony of physics that seemed to explain every light in the sky, from the faint glow of the Big Bang to the spiral arms of the Milky Way. We thought we had finally captured the laws of the heavens. But the harmony is breaking. The expansion Edwin Hubble first detected nearly a century ago has accelerated into a crisis that threatens to collapse our entire map of existence. We are at the edge where the math fails. The official story tells us that our understanding is nearly complete. Consensus claims that only minor details remain, but this narrative is a lie. Humanity has always loved a good story, and we wrote the Standard Model to be the final chapter of our cosmic origin. Unfortunately, the universe is not a polite narrator. Beneath the surface of the established story, a chasm is opening. Seemingly unconnected threads, from the first light of the Big Bang to the rotation of nearby stars, are pulling apart. We have found that our best model is more than incomplete. The architecture is broken. We will find that the very tools we use to measure reality are giving us 2 different answers for the same universe. We must now look into the gaps where the ghosts of new physics hide, waiting to be acknowledged by a civilization that thought the mystery was solved. In the chapters ahead, we will descend through the layers of this scientific collapse. Our journey begins with the expansion rate mystery, a conflict known as the Hubble Tension. Why does the beginning of time disagree with the present day? Next, we will examine the 5 sigma wall, the gold standard level of statistical proof that researchers have finally reached. From there, the investigation traces the failures of dark matter across individual galaxies through the ES8 growth tension. This anomaly reveals a fundamental mismatch between the matter density of the early universe and the structure of our modern neighborhood. We will then confront the ghost in the cosmic microwave background, known as the AL lensing anomaly, a signal that suggests the very shape of the universe might be different than we assumed. Finally, we face the dark sector, where dynamical energy and phantom physics await our recognition. We are no longer asking if the model is failing. Instead, we must ask if we are witnessing the birth of a new reality. We have reached the limits of the cage Edwin Hubble accidentally built. As we cross this threshold, we must choose between the comfort of our old maps and the terrifying beauty of a universe we no longer understand. The Standard Model is breaking, and in the cracks, a new cosmos is waiting to be born. Our investigation into these failures begins now. And if you are ready to explore these mysteries with me, hit that like button and subscribe. YouTube will help others like you discover this channel, and that means we are learning together. Let us dive in. That investigation leads us directly into a statistical battlefield. At the center of this conflict lies a single number, represented by the symbol H0. This number describes the Hubble constant, the rate at which the universe expands at this very moment. For decades, the pursuit of H0 was the holy grail of astronomy. If we knew the expansion rate, we could calculate the age of the universe, the distance to the furthest galaxies, and the ultimate fate of the cosmos. But when scientists finally got the tools to measure this number with extreme precision, the results did not bring clarity. They brought a paradox. To understand the scale of this problem, consider the two primary ways we measure the expansion of the cosmos. The first method is direct. We look at objects in the nearby universe, measure their distances, and see how fast they are moving away from us. This approach provides the local measurement. The second method is indirect. We look at the very early universe, specifically the light left over from the Big Bang, and use our best model of physics to predict what the expansion rate should be today. This approach provides the cosmological prediction in a universe that makes sense. These two numbers should be identical. If we measure the speed of the car with a radar gun and then calculate the speed of the car based on the revolutions of the engine per minute, the answers should match. But in cosmology, the radar gun says 73, while the engine calculations say 67. These two numbers are screaming at each other from across a gap that no one can explain. The universe appears to play a game of cosmic keep away, and the physicists are the ones left running in circles without their shoes on. The local measurement is the anchor of our immediate reality. To get this number, astronomers use what they call a distance ladder. Imagine trying to measure the length of a long road when you only have a 1-foot ruler. You measure 1 foot, mark the ground, then move the ruler. But eventually, the road becomes too long for the ruler. So, you use the ruler to calibrate a longer stick, maybe 10 feet long. Then you use the 10-foot stick to calibrate an even longer rope. Each step depends on the one before the previous step. In space, the first rung of this ladder is geometry. We use the orbit of the Earth to measure the distance to nearby stars through a shift called parallax. This shift is our ruler. The system is simple and elegant, provided you do not mind doing math that would make a supercomputer ask for a vacation. Once we have our geometric ruler, we use the model to measure a specific type of star called a Cepheid variable. These stars are remarkable because they pulse. They get brighter and dimmer with a rhythmic regularity that reveals their true intrinsic luminosity. This discovery traces back to Henrietta Swan Leavitt at the Harvard College Observatory in the early 1900s. Leavitt was one of the Harvard computers, a group of women hired to perform the grueling task of cataloging and analyzing thousands of glass photographic plates. While the male astronomers of the era focused on grand theories, Leavitt focused on the data. She meticulously tracked the flickering of stars in the small Magellanic Cloud, noticing a strange pattern. The brighter the star, the longer the period of the pulse. This relationship, now known as Leavitt's law, provided the first real way to measure distances across the void. Leavitt worked in an era when the university forbade women from using the great telescopes. While the men peered through the glass, the women of the Harvard College Observatory were confined to the analysis of the data they left behind. But Leavitt turned this restriction into a revolution. She realized that the stars were communicating through their flickering light. By cataloging over 2,000 variable stars, she identified a mathematical precision that transformed a chaotic sky into a predictable map. The pulses were not merely random events, they were the heartbeat of the cosmos, providing a rhythmic cadence that allowed us to step beyond our own galaxy for the first time. Her persistence in that quiet office provided the foundational physics for everything we know about the scale of the universe. Without her insight into the period-luminosity relationship, the expansion of the universe would have remained an unobservable theory. If you know how bright a star actually is, and you measure how dim the star appears from Earth, the math tells you exactly how far away the star resides. Henrietta Swan Leavitt realized that these pulses were not random noise. They were cosmic signals, ticking like clocks across the silence of space. Before this breakthrough, our sense of the scale of the universe was local and confined. Leavitt gave humanity the first yardstick capable of measuring the true distance to other galaxies. Her work transformed astronomy from a science of guessing into a science of precise measurement. Cepheids became our 10-foot sticks, and without her diligence in that cold Harvard office, the distance ladder would have remained a pile of disconnected rungs. But even Cepheids have limits. We can only see them in relatively nearby galaxies. To reach out into the deep flow of the expanding universe, we need a source much brighter. This gap is where Type 1a supernovae prove their worth. These are exploding stars, the massive detonations of white dwarfs that have stolen too much matter from a companion. Because these explosions always occur at a specific mass limit, they all have roughly the same peak brightness. They are the standard candles of the cosmos, visible across billions of light years. They are our longest measuring ropes. Of course, using a massive stellar explosion as a measuring tape presents drawbacks, mainly that you have to wait for a star to die before you can finish your homework. By climbing this ladder from parallax to Cepheids to supernovae, the Sheros team, led by Nobel laureate Adam Riess, arrived at a precise value for the Hubble constant. Their latest measurement, published in 2022, yields a value of 73.2 kilometers per second per megaparsec. This measurement means that for every megaparsec, roughly 3.26 million light-years of distance from Earth, a galaxy is moving away from us 73.2 kilometers per second faster. This result is the product of decades of refinement. The team has checked for dust interference, stellar aging, and instrumental bias. They have looked for every possible error, but the number remains stubbornly high. Now, consider the other side of the gap. This territory belongs to the cosmic microwave background, or the CMB. This radiation is the afterglow of the Big Bang, a snapshot of the universe when the model was only 380,000 years old. At that time, the cosmos was a hot, dense plasma where light and matter were inextricably linked. Sound waves, known as baryon acoustic oscillations, rippled through this primordial soup at nearly the speed of light, driven by the competing forces of gravity and radiation pressure. These oscillations left a permanent imprint on the distribution of matter and the pattern of temperature fluctuations across the entire sky, creating a cosmic yardstick that scientists can measure today with incredible precision. By analyzing this pattern, we can see the seeds of everything that exists today. To interpret this pattern, we use the Planck satellite, an instrument of incredible precision launched by the European Space Agency. The Planck data provides a high-definition map of the infant universe, capturing the subtle temperature variations that were frozen into the sky when the cosmos first became transparent to light. These fluctuations represent the physical conditions of the early universe, including the density of matter and the pressure of radiation. When scientists feed this high-resolution map into the standard model of cosmology, the mathematical framework utilizes the physics of the early plasma to predict what the expansion rate should be in our modern era. The Planck satellite is essentially a cosmic time machine with better resolution than your average home security camera. To achieve this level of clarity, the Planck satellite resides at the second Lagrange point, a gravitationally stable location 1.5 million kilometers from Earth. In the perpetual shadow of our planet, The instrument operates at temperatures only a few degrees above absolute zero. This extreme cold is necessary to detect the incredibly faint thermal signature of the early universe. The detectors are so sensitive that they could measure the heat of a candle on the surface of the moon from Earth. This level of precision allows us to see the tiny fluctuations in temperature, differences of less than 1 part in 100,000, that were the seeds of every galaxy we see today. The mission was a feat of engineering that required us to quiet the noise of the modern world to hear the whisper of the Big Bang. Every pixel on the Planck map represents a victory of human ingenuity over the immense silence of the void. The model assumes a flat universe, a specific amount of dark matter, and a constant amount of dark energy. Under these assumptions, the Planck data predicts a Hubble constant of 67.3 kilometers per second per megaparsec. Look at the discrepancy. The local universe says 73. The early universe predicts 67. This discrepancy is not a small difference. The discrepancy represents a 9% gap. In the world of high-precision cosmology, this discrepancy is a chasm. The failure returns us to our broken radar gun. Both the speedometer and the GPS are the most expensive, most accurate instruments ever built, but they are giving us two different speeds for the same car. Neither side is willing to back down. For years, the mainstream scientific community hoped this was just a measurement error. Perhaps the Cepheids were weirder than we thought. Maybe the Planck satellite had a subtle calibration glitch. If the error bars on these measurements were large enough, the two numbers might overlap and the tension would disappear. Scientists call this a systematic error, an unknown unknown that biases the data. But as the measurements improved, the error bars did not widen, they shrank. The escalating tension brings us to the 5 sigma wall. In physics, sigma is a measure of statistical significance. A 1 sigma result is a coin flip. A 3 sigma result is interesting, roughly a 1 in 700 chance of being a fluke. But 5 sigma is the gold standard. This value represents a 1 in 3.5 million chance that the result is a statistical accident. In the world of particle physics, 5 sigma is the threshold for a formal discovery. This threshold allowed researchers to confirm the discovery of the Higgs boson. Reaching 5 sigma is the scientific equivalent of winning the lottery while being struck by lightning on a Tuesday. In 2021, Adam Rees and the Sharrows team announced that the Hubble tension had crossed the 5 sigma threshold. The discrepancy was no longer a curious anomaly. The statistical weight of the evidence had become so heavy that the possibility of the model being a coincidence had effectively vanished. The two measurements are now formally in disagreement. The beginning of the universe and the present day are no longer on speaking terms. The mystery deepens when we realize that the standard model represents more than a mere guess. This framework stands as the most successful theory in the history of science. The model explains the abundance of elements, the formation of galaxies, and the large-scale structure of the entire universe. For 20 years, the model has passed every test we threw at the framework. But now, the model has hit a wall. If the model is correct, why does the model fail to predict the expansion rate of our own neighborhood? One possibility is that our distance ladder is broken in a way we cannot see. Imagine if the Cepheid stars in distant galaxies are fundamentally different from the ones nearby. Perhaps they have a different chemical makeup, or their environments affect their brightness in a way we have not accounted for. This uncertainty is the dark horse of the debate. If the local measurement is wrong, then the standard model survives. But the Sharrows team has spent 20 years trying to find this error. They have used different types of stars, like the tip of the red giant branch and different telescopes. While some methods give slightly different results, they almost all point toward a higher value than the Planck prediction. The other possibility is far more radical. If the local measurement is correct, then the standard model is incomplete. A component is missing from our understanding of the early universe. To close the gap, we would need to change the physics of the Big Bang. Perhaps dark energy is not a constant, but a force that changes over time. Or maybe an extra burst of energy occurred in the first few thousand years, a phenomenon researchers call early dark energy. This would act like a cosmic kick, pushing the universe to expand faster than the traditional model predicts. But adding new ingredients to the early universe is dangerous. This process resembles changing a recipe that has worked for a century. If you add too much of a new spice, you might fix the expansion rate, but you might ruin the formation of galaxies or the pattern of the CMB. The standard model is so tightly constrained that almost no room remains for adjustment. Every attempt to fix the Hubble tension with new physics creates new problems elsewhere. The math is a delicate house of cards, and we have just found a card that does not fit. Think about the implications of this failure. This standard model operates on the assumption of a simple, uniform cosmos. In this framework, dark energy is treated as a property of empty space, a constant pressure that never changes. Similarly, dark matter is modeled as a cold, invisible substance that only interacts through gravity. But the Hubble tension suggests that the dark sector, the 95% of the universe we cannot see, might be far more complex than we imagined. We might be looking at a universe that is dynamical, evolving, and full of hidden interactions. The pieces do not fit. We are standing at a threshold where the old maps no longer work. For nearly a century, we followed the fleeing galaxies that Edwin Hubble discovered, thinking we were nearing the end of the story. But instead of a conclusion, we found a contradiction. The expansion of the universe is telling us two different stories at once. One story is written in the light of the Big Bang, a tale of a predictable, orderly cosmos. The other story is written in the stars of our own sky, a tale of a universe that is moving faster than the model should. The discrepancy places us squarely within the domain of the 5 sigma wall. The model is a barrier of evidence that we cannot ignore. The model tells us that our understanding of the cosmos has a fundamental hole. We lack more than a mere detail. We are missing a principle. As we move deeper into this investigation, we have to confront the possibility that the standard model of cosmology is not the final answer. The model might just be the best approximation we have had so far. The true nature of the universe is still hiding in the gap between 67 and 73. This uncertainty is a gift. The gap signifies that fundamental truths still await discovery. The discrepancy ensures that the next generation of telescopes and experiments will do more than merely refine old numbers. They will be searching for the physics that exists beyond the standard model. They will be searching for the dark energy interactions, the sterile neutrinos, or the modified gravity that might explain why the universe is running away from us so quickly. We are living in the middle of a paradigm shift. The standard model of cosmology has served us well for decades, but the model has reached the limit of the framework. The paradox of H0 is a symptom of a deeper malaise in our understanding. The model suggests that our assumption of a simple, static lambda dark energy might be the root of the problem. If dark energy is not a constant, if the factor is something that changes, then the expansion history of the universe becomes far more complex. We would no longer be living in a vanilla cosmos. We would be living in a universe of dynamical forces that we have only just begun to sense. The fleeing galaxies that Edwin Hubble first saw are still moving, still expanding and still challenging us to understand their motion. The 5 Sigma wall is not the end of the story. The model is the beginning of a new investigation. We have found the anomaly. The data has been verified. Our investigation confirms that the pieces do not fit, and that represents the most exciting development that has happened to physics in a century. The search for the new physics begins, where the evidence is clear and the mystery is just beginning to unravel. No path leads back to the old certainty. The investigation now turns to the smallest scales of the dark matter problem. If the Hubble tension is the macro-scale failure, the cusp and core problem is the micro-scale failure. We will find that dark matter, the invisible scaffolding of the universe, is not behaving according to the rules of the standard model. The galaxies are hollow where they should be dense, and quiet where they should be crowded. The failure of the model extends beyond the expansion of the whole. The structural breakdown reaches into the heart of every single galaxy. That structural breakdown is where we go next. The pieces do not fit. And that point is when the mystery deepened. We are at the edge of the cage, and the universe is already outside. The investigation of the 5 Sigma wall is complete, but the investigation into the standard model is only getting started. The evidence is waiting, the data is clear, and the standard model is failing. But what happens when the math hits the reality of the small-scale universe? Let us look at the evidence. But that expansion mystery is just the first crack in the wall. While the cosmos screams at the largest scales, a different, quieter failure is happening right in our own backyard, specifically inside the individual building blocks of reality. As we look closer at these fundamental components, the pieces continue to drift apart. To understand why the mathematics of the cosmos is breaking, we must descend from the grand flow of the expanding universe into the heart of the galaxies themselves. This local neighborhood is where the invisible scaffolding of the universe, the dark matter, is supposed to hold the structure together. But in the local neighborhood, the scaffolding is showing deep structural cracks. The evidence suggests that the very nature of dark matter is not what our models predicted. What happens when the most successful theory in history cannot explain the shape of a single galaxy? Let us look at the evidence. In the late 1970s, the scientific community faced a silent revolution. Astronomers like Vera Rubin and Kent Ford were trying to understand how galaxies rotate. The assumption was that galaxies behaved like solar systems, where planets move slower as distance from the central mass increases. But when Rubin and Ford measured the Andromeda galaxy, the data refused to cooperate. Instead of falling velocities, the researchers saw rotation curves that remained flat. Stars at the outermost reaches were moving as fast as stars near the center. This unseen mass became known as dark matter. The discovery set the stage for a conflict over where this dark matter resides within a galaxy. The mechanics of rotation depend on mass distribution. In the standard model, this galactic mass is dominated by cold dark matter, assumed to be collisionless and non-relativistic. Because these particles only feel gravity, the particles should sink toward the center of the gravitational potential well, creating a dense environment in the heart of every galaxy. Small clumps of dark matter merge to form larger halos, and during these mergers, the particles lose energy and concentrate in the middle. If the mass is concentrated in a sharp peak, the gravitational force is intense, requiring stars to move at very high speeds to avoid falling inward. By comparing observed velocities to predictions, researchers map the invisible dark matter halo, which typically outweighs the visible matter 10 to 1. This scaffolding drives galaxy formation, yet on scales smaller than 1 megaparsec, the models deviate from reality. The tension between predicted and observed dark matter is like the difference between a high-speed carousel and a spinning top. On a carousel, horses at the outer edge must move faster than those near the center to complete a circle in the same time. This represents solid body rotation, where mass is distributed evenly. A spinning top, however, has most weight concentrated in a tiny point. The standard model predicts galaxies should behave like the top, with a massive point of dark matter at the center. However, dwarf galaxies behave like the carousel. Mass is spread out in a uniform way, suggesting dark matter does not pile up as expected. The carousel of stars moves through a gravitational field far less intense than the theoretical top we built in simulations. This distribution is the first signal that the standard model is failing to describe the internal architecture of the universe. The anomaly becomes truly unavoidable when we look at the smallest galaxies in our neighborhood. These systems, known as dwarf galaxies, are the most dark matter-dominated objects in existence. In many of these systems, the dark matter outweighs the visible matter by a factor of 1,000. Because these galaxies have so few stars, the gravity of the dark matter is the only force that matters. This makes dwarf galaxies the perfect laboratories for testing the standard model. If the model is correct, these small systems should have the most concentrated centers of all. But researchers like James Bullock and Michael Boylan-Colchin have found that the reality is the exact opposite. The centers of these galaxies appear hollowed out. According to a paper by Bullock in 2017, the observed number of small galaxies in the local group is far below the count of low-mass dark matter halos predicted by simulations. This density mystery transcends a simple count of missing objects. The finding represents a fundamental problem of missing mass. Even when we find the galaxies that do exist, the dark matter at the centers of the galaxies is less dense than the math requires. If dark matter only interacts through gravity, nothing should be able to stop the particles from piling up in the center. The fact that the centers are quiet and spread out implies that either our understanding of gravity is wrong, or dark matter has hidden properties that we have completely ignored. The pieces do not fit, and the failure is happening right in our own cosmic backyard. This failure on small scales forces us to confront a humbling reality. We have built a model of the universe that works perfectly for the largest structures, like clusters of galaxies and the cosmic web, but fails to describe the very things we can see most clearly. If the standard model cannot correctly predict the structure of a single galaxy in our own neighborhood, how can we trust the predictions of the model for the nature of the entire cosmos? The evidence suggests that our invisible scaffolding is not what we thought the scaffolding was. We are like architects who have designed a skyscraper that stands tall, but whose individual rooms are built with the wrong dimensions. The building might look fine from a distance, but the internal structure is a mess. This failure is a signal that our fundamental assumptions about the dark sector are incomplete. The mystery of the missing density is an invitation to look for a new physics that can account for the quiet, spread-out reality of the galaxies we call home. But a deeper complication exists. The problem transcends the total mass. The investigation focuses on the geometric distribution of the dark matter itself. This brings us to the first major contradiction in the internal structure of galaxies, a mystery known as the cusp core problem. In the mid-1990s, a team including Giulio Navarro, Carlos Frenk, and Simon White identified a universal shape for dark matter halos. This shape, known as the Navarro-Frenk-White profile, or NF-U profile, appeared in every simulation, regardless of the size of the galaxy or the history of galactic formation. Whether the researchers simulated a tiny dwarf galaxy or a massive cluster, the dark matter always distributed the particles in the same way. This discovery was hailed as a triumph for the Standard Model. The NF-U profile became the gold standard for comparing theoretical models to observational data. For several years, the scientific community believed that the mystery of dark matter distribution was solved. But as the resolution of our telescopes improved, the elegance of the profile began to clash with the messy reality of the sky. What began as a universal law soon transformed into one of the most persistent and frustrating problems in modern physics. The defining characteristic of the Navarro-Frank-White profile is the existence of a central cusp. In mathematics, a cusp occurs when the density of a substance increases rapidly as you move toward the center, reaching an extremely high value at the point of origin. For a dark matter halo, this means the density profile follows a relationship where the mass increases as 1 over the radius. This concentration is a direct consequence of the cold, collisionless nature of the dark matter particles. Because these particles do not have any way to exchange energy other than gravity, the particles cannot bounce off each other. As the halo forms, the particles simply fall deeper into the center, creating a sharp, needle-like peak of density. Scientists measure this density by observing the velocity of gas clouds near the galactic center. If a cusp is present, the velocity of the gas should rise very sharply as one moves away from the center. However, when astronomers perform these measurements with high-precision radio telescopes, the researchers do not see a sharp rise in velocity. Instead, the velocities rise slowly and then level off. This slow rise indicates that the density at the center is constant rather than increasing. The sharp needle of the cusp is missing, replaced by a flat, uniform distribution of mass. The difference between a cusp and a core is the difference between a pointed pyramid and a flat plateau. Imagine you are building a structure out of sand. If you pour the sand from a single point, the sand naturally forms a steep pointed cone or pyramid. This is the cusp. The shape is the natural result of gravity, acting on individual grains that have no other way to interact. Now, imagine you are looking at that same pile of sand, but instead of a point at the top, someone has flattened the pile into a wide, level plateau. To get a plateau, some force must have intervened to stop the pyramid from forming. In the world of galaxies, the Standard Model says that gravity should build a dark matter pyramid in the center of every system. But when we look at the actual galaxies, we see plateaus. We see these flat cores where the density is the same for thousands of light years across the center. This discrepancy is the cusp core problem. The problem represents the mystery of the missing pyramid. A hidden mechanism in the physical universe is preventing the dark matter from piling up, but the Standard Model does not include any mechanism capable of doing that. The plateau exists, and our current maps have no way to explain how the formation occurred. The evidence for these plateaus became undeniable with the Little Things survey, led by Sihon O. By using the Very Large Array Radio Telescope, the team mapped the motions of neutral hydrogen gas in nearby dwarf galaxies. The O survey found that in galaxy after galaxy, the density profiles were flat. These were more than minor deviations from the Navarro-Frank-White profile. The observations were total contradictions. In a paper published in 2015, the team demonstrated that the observed rotation curves were better fit by a model with a constant density core than by any version of the Standard Model. This finding is particularly problematic for galaxies that are dominated by dark matter. In larger galaxies, like the Milky Way, some scientists argue that the explosion of supernovae could push the dark matter out. But in these tiny dwarf galaxies, not enough stars exist to produce that much energy. The mountain of dark matter should be immovable. Yet the data shows the mountain has been shifted. If dark matter cannot be moved by the stars, then perhaps the dark matter is moving itself. The mystery deepens when we realize that the plateaus appear to be a universal feature of the small-scale universe. This raises a terrifying question for the Standard Model. If the most successful theory of cosmology cannot predict the basic shape of the most common galaxies, then how much of the theory is actually true? We are looking at a fundamental mismatch between our best simulations and our best observations. The dark matter pyramid is a ghost haunting the halls of theoretical physics, while the real world is built on plateaus. This failure represents more than a technical detail. The anomaly indicates that our fundamental understanding of the dark sector relies on a false premise. That brings us to the next clue in the investigation, a problem that goes beyond the shape of the center and reaches into the very population of the dark matter halos. In 2011, a new crisis emerged that threatened to undermine the entire hierarchical structure of the Standard Model. While the cusp core problem focused on the shape of dark matter, this new anomaly focused on the mass of the most powerful subhalos. Researchers Michael Boylan-Colchin, James Bullock, and Manoj Kaplinghat were analyzing the results of the Aquarius project, which simulated the small clumps of dark matter that orbit larger galaxies, known as subhalos. According to the Standard Model, these subhalos should be the birthplaces of the satellite galaxies we see orbiting the Milky Way. The researchers expected the most massive subhalos in the simulation to match the most massive satellite galaxies in the real sky. But when the team compared the simulated subhalos to the observed data, the researchers found a massive discrepancy. The most massive subhalos in the computer were significantly denser and more powerful than anything we see in reality. This density discovery was named the too big to fail problem. The findings suggested that either the most massive subhalos in our neighborhood are mysteriously empty, or our understanding of how these halos form is fundamentally broken. The mechanics of the too big to fail problem are rooted in the relationship between mass and velocity. To measure the mass of a satellite galaxy, astronomers look at the velocity dispersion of the stars of the galaxy. In the Aquarius simulations, the Standard Model predicts that a Milky Way-sized galaxy should be surrounded by at least 10 subhalos that are extremely massive. These halos are so massive that the structures should be virtually immune to the effects of supernova feedback. The halos have the gravitational depth to hold onto the gas of the halos and build bright galaxies. However, when we look at the actual satellite galaxies orbiting the Milky Way, we do not find these massive systems. The brightest satellites we see, like Draco or Sculptor, reside in halos that are much less dense than the ones predicted by the simulation. The internal velocities of the real stars are significantly lower than the velocities predicted for the most massive subhalos. This means that the massive subhalos that should exist either fail to form galaxies at all, or the subhalos are somehow much less dense than the Standard Model requires. The too big to fail problem is like walking into a room that is supposed to be filled with professional basketball players, but finding only elementary school children. Imagine you have a blueprint that explicitly states the 10 tallest people in the city will be in that room. You walk through the door, expecting to see giants who are too big to be overlooked. But instead, the room is occupied by children who are barely 4 feet tall. The chairs designed for the tall guests are empty. This is the situation cosmologists face with the satellite galaxies of the Milky Way. The Standard Model is the blueprint that predicts the presence of massive dark matter giants. These giants should be the brightest, most obvious galaxies in our local group. But when we look into the dark matter room, we only see the children. The massive subhalos that the model says must exist are either invisible or the halos have somehow been shrunk down to a fraction of the predicted size. The mystery deepens when we realize that the traditional excuses for missing galaxies do not apply here. While tiny halos might stay dark because the structures lack the gravity to hold onto gas, this explanation fails for the systems at the heart of the too big to fail problem. These halos are so massive that the subhalos should be resistant to almost any form of disruption. Investigations into the Andromeda Galaxy and into isolated dwarf galaxies have shown that the problem is widespread. As James Bullock noted in 2017, the same mismatch between simulated density and observed density persists across the local universe. This pattern is a systemic failure. The Standard Model is consistently over-predicting the density of the most massive small-scale structures. This tension suggests that the dark matter particles are not behaving like the cold, inert points of mass we assumed. If the giants are missing, the absence might be because the dark matter itself is softer or more spread out than the model allows. So how much of this is true? Well, here is what holds up. The evidence for the small-scale crisis is real and verified across multiple independent surveys. The cusp core problem and the too-big-to-fail anomaly are more than measurement errors. The problems are formal discoveries of a failure in the collisionless assumption of the Standard Model. What remains genuinely unexplained is the mechanism behind this failure. If the stars cannot push the dark matter around, then what is really going on? This brings us to the most exciting possibility in modern cosmology: the idea that dark matter is not as lonely as we thought. In the year 2000, David Spergel and Paul Steinhardt proposed a radical departure from the Standard Model. The researchers realized that these persistent failures on small scales could be solved if dark matter particles were not as isolated as we assumed. The researchers called this idea self-interacting dark matter, or SIDM. This was a bold move, because the proposal added complexity to a model that was prized for simplicity. However, the proposal gained momentum as the small-scale anomalies refused to go away. The possibility that dark matter particles interact with one another, having a hidden internal life with a specific set of rules, provided a natural way to explain why galaxies were less dense than expected. The mechanics of self-interacting dark matter are based on the concept of a scattering cross-section. This value is a measure of how likely two particles are to collide. If the cross-section is 0, the particles never interact, which is the assumption of the Standard Model. But if the cross-section is greater than 0, the particles can exchange energy and momentum through collisions. In the dense centers of galaxies, these collisions become frequent. Over millions of years, these constant collisions act like a heat source, pushing the dark matter particles outward from the center. This outward pressure prevents the density from building up into a sharp cusp. Instead, the pressure creates a flat, uniform core. The mechanism addresses the too-big-to-fail problem by reducing the overall density of the most massive subhalos, bringing the subhalos into agreement with the observed satellite populations. The math of SIDM is governed by the ratio of the cross-section to the mass of the particle. The transition to self-interacting dark matter is like the difference between a crowd of ghosts and people in a busy subway station. Ghosts can pass through one another and all occupy the same space, If an attraction exists in the center, all the ghosts would pile up in a dense, overlapping mass. This is the cusp of the standard model. But real people have physical bodies and bump into each other. If the center gets too crowded, people naturally push each other outward. These collisions create a uniform distribution where density is limited by the physical size of the crowd. This plateau is the core of self-interacting dark matter. Internal pressure turns the pointed pyramid of the standard model into the flat plateau of reality. Dark matter is no longer a collection of lonely ghosts, but a crowded room where the particles are constantly negotiating for space. The controversy surrounding self-interacting dark matter lies in the potential of the model to break the successes of the standard model on large scales. If the dark matter interacts too strongly, the interaction could wash out the delicate features of the early universe. Some scientists argue that baryonic physics, like the effects of gas and stars, might still be enough to explain the small-scale crisis. This creates a fundamental tension. Is the failure of the standard model a sign that we need a more complex dark sector? Or is the failure just a sign that we do not yet understand the complex interaction of gas and stars? As the data from surveys, like the Dark Energy Spectroscopic Instrument, continues to pour in, the room for traditional explanations is shrinking. The anomalies are not going away, and the case for a self-interacting dark sector is becoming harder to ignore. The possibility of self-interacting dark matter changes how we view our place in the cosmos. The possibility suggests that we are residing in a universe that is far more vibrant, interactive than we ever imagined. The standard model is far from the final word. The model represents merely the first chapter of a much larger story. We are standing at the threshold of a new understanding, where the failures of our old models are the keys to a deeper truth. The pieces do not fit, and that is the most beautiful thing about the search. The silence of the dark sector is finally being broken by the evidence of the internal life of the dark sector. The investigation into the small-scale crisis reveals that the cracks in the model are more than confined to the expansion of space, but reach into the very hearts of the galaxies we call home. But as we look deeper into the foundations of our cosmic map, we find that the most successful data of all, the afterglow of the Big Bang itself, is starting to show new ghosts. That is where we go next, to the cosmic microwave background, and the signal that should not exist. That impossible signal, the phantom that defies our most basic cosmological rules, does not hide in the dark corners of the sky, but in the very light that serves as our foundation. To understand why the standard model is failing, we must now move beyond the local galaxies and examine the deepest archive of human knowledge, the cosmic microwave background. This afterglow of the Big Bang is often called the gold standard of cosmology. The light from this era has traveled for over 13 billion years, carrying a perfect record of what the universe looked like at the moment of cosmic recombination. For decades, researchers considered this map unassailable. But as our measurements have reached a new level of precision, the gold standard is starting to exhibit an internal friction that the community cannot ignore. The pieces do not quite fit, and the contradictions are coming from inside the house. The first major contradiction in this cosmic record involves how the universe has grown from a smooth, hot plasma into the complex web of galaxies observed today. This structural mystery is known as the ES8 tension, or the growth tension. The story of this discovery begins with the Planck satellite. As we have seen, this Planck mission was designed to map the temperature fluctuations of the early universe with incredible accuracy. But as the cosmic map became clearer, the modern universe started to look wrong. Researchers like Eleonora di Valentino, a prominent cosmologist at the University of Sheffield, and Hendrik Hildebrand, leading the kilodegree survey, began to notice a discrepancy that would soon threaten the very foundation of structure formation. While the Planck satellite provided the initial conditions of the universe, a new generation of wide-field surveys was beginning to map the modern result. The kilodegree survey, or KIDS 1000, used the VLT survey telescope in Chile to examine over 1,000 square degrees of the sky. This KIDS 1000 survey transcended the scope of a simple telescope project. The endeavor was a monumental effort of international collaboration. Using the VLT survey telescope, a state-of-the-art instrument located at the Paranal Observatory in the Atacama Desert, the team spent years capturing images of the southern sky. This Atacama environment is one of the most hostile and beautiful places on Earth, a high-altitude plateau where the air is so dry and the sky is so clear that the stars do not seem to twinkle, but rather burn with a steady, unblinking intensity. The heart of this telescope is OmegaCam, a massive 268-megapixel camera that can see light in multiple wavelengths. This VLT instrument is not merely a piece of hardware. The camera is a technological masterpiece containing 32 individual CCD detectors that work in perfect synchronization to capture an area of the sky 4 times the size of the full moon in a single exposure. This observational detail is staggering, allowing the camera to detect the subtle, distorted shapes of galaxies that are billions of light years away. This OmegaCam camera allowed the researchers to measure the shapes of galaxies with a precision that was previously impossible. Every night, the telescope would sweep across the sky, collecting gigabytes of data that were then processed by supercomputers in the Netherlands and Italy. The goal was to build a map of the dark matter scaffolding that was so detailed that any deviation from the standard model would be immediately apparent. This scientific rigor gave the ESA tension. When Hendrik Hildebrand and his colleagues published their findings, the results were based on the analysis of the growth of structure. Meanwhile, the Dark Energy Survey was performing a similar feat using the 4-meter Blanco telescope in the Andes. These missions were not looking at the distant afterglow of the Big Bang. Instead, these missions were focusing on the modern cosmic web, measuring how much matter has clumped together over 13.8 billion years of gravitational collapse. By 2013, the first signs of trouble appeared. The clumping of matter was not matching the predictions derived from the Planck satellite. This data mismatch was the birth of the growth tension, a signal that the universe is smoother and less concentrated than our best theories allow. The mechanics of this investigation are centered on a single value known as the ES8 parameter. This S8 value is a crucial metric that represents the amplitude of matter fluctuations on scales of 8 megaparsecs, a distance roughly equivalent to 26 million light-years. This S8 parameter is not a simple measurement. The parameter is a combination of the total matter density of the universe and the strength of the fluctuations within that matter. To measure this parameter locally, astronomers rely on a technique known as weak gravitational lensing. Because mass bends the path of light, the massive clusters of dark matter in the modern universe act like subtle, invisible lenses. As the light from millions of distant galaxies travels toward our telescopes, the light is slightly distorted by the gravitational pull of the cosmic web. By painstakingly measuring the shapes of galaxies and accounting for these distortions, scientists can reconstruct the 3-dimensional scaffolding of the dark matter. The mechanical conflict revealed by this technique is stark. The Planck data, representing the recipe of the infant universe, predicts a modern-day clumping value that is consistently higher than the value measured by the weak lensing surveys. To understand why this discrepancy is such a problem, we must look at the linear and non-linear scales of structure growth. In the early universe, gravity is a simple, linear process. But as time passes and matter clumps together, gravity becomes non-linear and complex. The standard model uses the linear growth observed in the afterglow to predict the non-linear clumping we should see today. The fact that the prediction fails suggests that our understanding of the transition from linear to non-linear growth is incomplete. The universe should be a crowded room of massive dark matter structures, but the surveys show an environment that is surprisingly sparse and quiet. This clumping discrepancy between the predicted and observed growth is like the difference between a recipe and the final cake. Imagine a perfect recipe from a legendary chef that tells you exactly how much yeast to use and how long the dough should rise. Based on those instructions, you expect a massive fluffy loaf of bread that dominates the kitchen table. You followed the instructions perfectly. Every gram of flour was weighed. Every second of rising time was monitored. Yet, when you open the oven door, you find a flat, dense pancake. The cake is not rising as the recipe demands. In this cosmic kitchen, the Planck satellite provides the recipe. The satellite tells us the exact proportions of dark matter, dark energy, and baryons that existed shortly after the Big Bang. Based on these ingredients and the laws of gravity, the universe should have built a structure filled with massive, dense clusters. But the weak lensing surveys show us the final cake, and the cake is flat. This sparse environment is particularly problematic. The universe appears to be missing the structural height and the clumping intensity that the standard model requires. Comparing the early universe to the modern-day structure is like checking a height chart for a child. If the growth chart predicts the child should be 6 feet tall by age 18, but the child stops growing at 5 feet, you do not ignore the chart. You start asking deep questions. Has the child been skipping meals? Is there a hidden biological factor that the chart failed to account for? Or perhaps the chart was written for a different species entirely. In this case, the universe seems to have stopped growing structure as the cosmic growth chart predicted. No matter how many times the researchers recalibrate the tools, the pancake persists. The clumping is simply not there. The anomaly is statistically significant, consistently hovering around the 3 sigma level. While 3 sigma is not the 5 sigma gold standard required for a formal discovery, the persistence of the signal across multiple independent surveys makes the situation impossible to dismiss as a simple mistake. According to a comprehensive update by Parivallaropoulos and Skara in 2022, the ES8 tension is a fundamental challenge to the conjoined history of the universe. In the standard model, the expansion of the universe and the growth of structure are 2 sides of the same coin. If you change one, you must change the other. The fact that the clumping does not match the expansion history suggests that either our understanding of dark matter is incomplete, or the laws of gravity are behaving differently than Einstein predicted over cosmic timescales. The scaffolding of the universe is weaker than the mathematics says the scaffolding should be. This structural failure on cosmic scales forces us to confront a humbling possibility. If the growth of structure is slower than predicted, the universe might be reaching a state of structural exhaustion. The invisible threads of dark matter that bind the galaxies together appear to be fraying. This clumping tension represents more than a problem for theorists. The situation is a challenge to our understanding of the ultimate fate of the cosmos. If the recipe for structure is wrong, then our predictions for the future of the cosmic web are also likely to be incorrect. The mystery of the S8 tension is an invitation to reconsider the fundamental laws that govern how matter organizes itself across the vastness of space. But as we look deeper into the Planck data, we find that the growth tension is only the beginning of the internal friction. The map itself contains a signal that contradicts the very geometry of our model. That brings us to the next clue in the investigation. An internal mystery involves a parameter known as AL, or the lensing amplitude. In the standard model, AL must be exactly equal to 1. This AL parameter represents the amount of gravitational lensing that the light of the afterglow experiences as the light travels to our telescopes. Because we know the contents of the universe from the CMB peaks, we can calculate exactly how much that light should be bent by the matter the light passes along the way. If AL equals 1, the theory and the data are in perfect harmony. But when the Planck team analyzed the final data release in 2018, the researchers identified a signal that should not exist. The value of AL was not 1. Instead, the value was significantly higher, reaching a level of approximately 2.8 to 3.5 sigma above the predicted value. The mechanics of the AL anomaly are found in the smoothing of the acoustic peaks. When we look at the power spectrum of the cosmic microwave background, we see a series of peaks and valleys that represent the oscillations of the early plasma. Gravitational lensing acts on these peaks by smoothing them out, much like a frosted glass pane blurs the sharp edges of an image. The more matter the light passes through, the smoother the peaks become. The Planck data shows an excess of this smoothing. The peaks are flatter than the standard model allows for a flat universe. To account for this extra blurring, the model is forced to conclude that more gravitational lensing exists than the available matter should allow. This excess smoothing is a direct contradiction. Looking at a blurry photograph and realizing that the lens was clean and the subject was perfectly still, yet the image is still out of focus, captures the essence of this mystery. The difference between the expected and observed lensing is like trying to drive through a fog that is thicker than the weather report predicted. Imagine you are driving on a clear night and you identify exactly 3 small patches of mist between you and your destination. You expect your vision to be slightly obscured 3 times. But as you drive, you find yourself in a dense, heavy fog that never seems to lift. You check your sensors, and the sensors insist the air is clear, yet your eyes see nothing but gray. To explain the fog, you have to assume that either your sensors are lying about the humidity, or the very light of your headlights is being scattered by a substance that your sensors cannot detect. In the Planck data, the excess lensing is the fog. The standard model is the sensor that says the air should be clear. The excess smoothing of the peaks is the evidence that the sensors are missing a fundamental part of the environment. That brings us to an uncomfortable realization. If the lensing is too high, the simplest explanation within the framework of general relativity is that the universe contains more matter than we thought. But adding more matter would break the agreement with every other part of the data. To fix the AL anomaly, researchers like Alessandro Melchiori, a leading cosmologist at the University of Rome, have suggested that we might need to change the very shape of the universe. This preference leads to an even bigger problem. The excess lensing can be explained if the universe is not flat, but closed, like the surface of a giant sphere. This spherical possibility, however, is a direct violation of the flat universe assumption that has been the foundation of cosmology for over 40 years. So how much of this is true? Well, here is what holds up. The AL anomaly is a robust feature of the Planck temperature data. No matter how the data is cleaned or reanalyzed, the excess smoothing remains. The internal consistency of the Planck data is under threat. What remains genuinely unexplained is why the temperature-power spectrum prefers a closed universe while the lensing reconstruction, a different part of the same data, prefers a flat one. The map is arguing with the map. This lensing anomaly is a direct contradiction. The situation is a sign of a systemic crisis in the gold standard of our field. If we cannot trust the internal consistency of the Planck data, the foundation of the standard model begins to crumble. The mystery of the AL anomaly deepens when we realize that the excess lensing represents more than a technical detail. The anomaly has profound implications for the mass of the neutrino. Massive neutrinos suppress the growth of structure because the neutrinos move too fast to be easily captured by gravity. This suppression should reduce the amount of lensing. But because Planck sees too much lensing, the model is forced to push the neutrino mass lower and lower to compensate for the blur. This conflict over neutrino mass is a perfect example of how the standard model is starting to tear at the seams. In the quiet town of Leopoldshafen, Germany, a massive experiment known as CATRIN is attempting to weigh the neutrino. The CATRIN spectrometer is a giant silver vessel that looks like a submarine, and the vessel is designed to measure the energy of electrons emitted during the decay of tritium. By looking at the highest energy electrons, the researchers can determine the mass of the neutrino that was left behind. As of 2022, the CATRIN experiment has set an upper limit of 0.8 electron volts. While this sounds tiny, this value is a giant compared to the limits coming from the Planck satellite. To put this in perspective, a single electron volt is approximately 1/billionth of the mass of a proton. The neutrino is so light that for decades, scientists believed the particle had no mass at all. But the laws of particle physics require the neutrino to possess mass, even if the weight is only a fraction of an electron volt. This discrepancy marks the point where the conflict becomes explosive. The Planck satellite measures the gravitational effect of neutrinos on the largest scales of the universe. If neutrinos were heavy, the neutrinos would have prevented matter from clumping together in the early universe, effectively washing out the fine details of the cosmic web. Because we see those details clearly, Planck concludes that neutrinos must be incredibly light. This discrepancy leads us to the final clue at this stage of our descent, the curvature crisis. For decades, the inflationary theory proposed by physicists like Alan Guth and Andre Linde has predicted that the universe must be flat. This flatness means that if you were to draw a giant triangle across the cosmos, the angles would add up to exactly 180 degrees. The theory of inflation was a revolution in physics because this theory solved the horizon problem and the flatness problem by suggesting that the universe underwent a massive expansion in the first tiny fraction of a second. This expansion would have smoothed out any initial curvature, leaving us with a flat cosmos. This condition is an absolute requirement for the standard model to work. But the excess lensing we just discussed has a terrifying side effect. When researchers allow the curvature of the universe to be a free parameter in the Planck analysis, the data does not choose 0. Instead, the data chooses a negative value for the curvature parameter, known as omega k. This preference implies that the universe is closed, shaped like a 4-dimensional ball. According to a paper by Valentino, Melchiori, and Silk in 2019, the evidence for a closed universe in the Planck temperature data is significant, reaching a confidence level of over 99%. The mechanics of a closed universe would transform our entire cosmological map. In a closed cosmos, the total energy density is greater than the critical density required for flatness. This extra density provides the gravitational pull needed to account for the excess lensing seen in the IL anomaly. But a closed universe creates an immediate and violent conflict with other datasets. Specifically, this situation clashes with the baryon acoustic oscillations data we discussed earlier. The measurements of the sound horizon scale from galaxy surveys like BOSS and eBOSS are only consistent with a flat universe. If the universe is truly closed, then the BAO measurements are wrong. But if the universe is flat, then the Planck temperature data is wrong. This deadlock represents the curvature crisis. This situation is an absolute deadlock between the two most successful methods of measuring the cosmos. The conflict between flatness and curvature is like two master mapmakers arguing over whether the Earth is a flat plane or a round globe. One mapmaker points to the local survey of a small field and shows that every line is perfectly straight. This local dataset represents the BAO data looking at the relatively local universe. The other mapmaker points to the horizon and shows how the light of the setting sun curves around the edge of the world. This horizon visualization represents the Planck data, looking at the furthest possible scale. Both mapmakers are using the best tools available. Both have performed their measurements with incredible precision. Yet, the mapmakers cannot agree on the fundamental shape of the ground they are standing on. To accept one map, you must discard the other. In modern cosmology, no middle ground exists. The universe cannot be both flat and closed at the same time. That brings us to the conjoined history problem. This conjoined history realization is the understanding that we cannot fix one tension without making the others worse. If we try to solve the Hubble tension by changing the expansion rate, we often increase the ES8 tension. If we try to fix the AL anomaly by assuming a closed universe, we create a massive curvature tension with the BAO data. The standard model is like a suit of armor that has become too small for the person wearing the suit. Every time we try to adjust one plate to make the suit comfortable, another plate pops off or restricts movement elsewhere. The armor is rigid and the data is growing. The internal friction within the Planck data is a signal that the lambda CDM framework is no longer flexible enough to contain the reality we are observing. So, case closed. Is the universe closed and the model dead? Not so fast. Some researchers argue that the AL anomaly and the preference for curvature are just statistical fluctuations or the result of undetected systematic errors in how the Planck cameras were calibrated. But the signal has persisted through every major data release, as we have moved from the 2013 data to the 2018 release, and now to the latest reprocessing known as NPipe. The tension remains. We have cleared away the noise, and what is left is uncomfortable. The gold standard map of the universe is showing us a ghost that should not exist. The pieces do not fit. And the mystery is no longer about the expansion of space, but about the very shape and growth of reality itself. We are standing at a threshold where our most trusted tools are giving us a warning. The standard model is breaking, and the next step of the investigation will take us into the dark sector, where the ingredients of the universe itself are starting to change to the phantom energy and the dynamical dark sector. That is where the truth awaits. The dark sector of the universe has long been treated as a static graveyard, a collection of silent, unchanging forces that govern the background of existence. For decades, the standard model assumed that dark energy was a mere number, a constant property of the vacuum that never varied across the vastness of time. But as the investigation into the standard model failures deepens, the data from the newest generation of observatories suggests that this graveyard is coming to life. The ingredients of the cosmos appear to be changing, shifting their behavior in ways that the cosmological constant simply cannot explain. We are entering a regime where the dark sector is no longer a passive background, but a dynamic and perhaps even interacting system that defies the very foundations of the Lambda-CDM framework. The first major sign of this dark sector escalation arrived in the spring of 2024, when the Dark Energy Spectroscopic Instrument, or DESI, released the results of the first year of the mission. Located at the Kitt Peak National Observatory in Arizona, the DESI instrument is a technological titan designed for one specific task: mapping the expansion history of the universe with a level of precision that was previously unthinkable. The heart of this instrument is a focal plane occupied by an army of 5,000 robotic positioners. Each of these robots holds a single fiber optic cable that can be precisely pointed at a galaxy or a quasar. This DESI masterpiece of precision engineering consists of a circular array where every millimeter is occupied by the mechanical architecture of the sensors. These robots are not merely static holders. The robots are dynamical agents of measurement, each capable of pivoting with a precision measured in microns to align a fiber optic cable with the light of a galaxy millions of light years away. The cables themselves are like glass tentacles, stretching from the back of the telescope to the spectrographs, carrying the ancient photons that have traveled for billions of years. Inside the dome at Kitt Peak, the environment must be meticulously controlled to prevent thermal expansion from throwing off the alignment of the robots. The researchers have effectively built a robotic eye that can see the entire history of the universe in a single night. This innovative design allows the telescope to capture the spectra of 5,000 cosmic objects simultaneously, effectively turning the observatory into a high-speed data factory for the history of space and time. This high level of automated observation has allowed the DESI team to collect more data in 1 year than all previous galaxy surveys combined, creating a high-definition record of the cosmic expansion that leaves no room for the errors of the past. To truly appreciate the weight of the DESI findings, we have to look closer at the yardstick the researchers used to measure the expansion of the universe. To map this grid, researchers rely on those foundational sound waves known as the baryon acoustic oscillations. By mapping the positions of millions of galaxies across a range of redshifts, the DESI team could measure how the expansion rate of the universe has changed over the last 11 billion years. This mapping process is like looking at a series of snapshots of a growing balloon that has been marked with a grid of known dimensions. By measuring how that grid stretches, we can reconstruct the expansion history of the balloon with incredible accuracy. The DESI mission is currently the most ambitious attempt to map this grid. The survey covers over 1/3 of the entire sky and will eventually map the positions of 40 million galaxies and quasars. This massive level of data is what allowed the team to identify the subtle shift in the dark energy behavior. Without the 5,000 robotic positioners working in perfect synchronization, the signal of dynamical dark energy would have remained buried in the noise. This DESI investigation has shown that when we use the most precise yardstick available to humanity, the results refuse to align with the standard model. The BAO signal is a physical record of a universe that is expanding in a way that the cosmological constant cannot accommodate. The moment of discovery for the DESI team came when the researchers analyzed the sonic echoes that define the expansion history. The survey traced the distribution of matter through the vastness of the cosmos, allowing the collaboration to chart the expansion history with unprecedented clarity across nearly the entire age of the universe. When the lead researchers, including figures like Michael Levi and the massive international collaboration of physicists, looked at the combined data from DESI, the cosmic microwave background, and Type 1a supernovae, the result was a shock to the scientific community. The expansion history did not match a constant dark energy. Instead, the data showed a statistical preference for a dynamical dark energy. But what if the driver is not following the map? The mechanics of this evolving energy are expressed through a concept known as dynamical dark energy. In the standard model, dark energy is represented by the cosmological constant, lambda. This equation value means that the energy density of space remains constant, even as the volume of the universe increases. However, the DESI results suggest that the value of W is not fixed. To investigate this possibility, physicists use a mathematical framework called the Chevalier-Pulaski-Linder parameterization. This parameterization method splits the dark energy behavior into two parts: W0, the value today, and WA, the rate at which that value changes as the universe expands. The mechanical revelation from the DESI survey is that the universe appears to prefer a quadrant of the W0 and W a plane that the standard model forbids. The data indicates that dark energy may have been stronger in the past and is weakening today, or perhaps even crossing a fundamental threshold known as the phantom divide. If the value of W passes below -1, the dark energy becomes phantom energy, a theoretical substance that becomes more dense as the universe expands. This behavior is a direct contradiction of the cosmological constant. The precision of the DESI measurements is so high that this statistical level of significance reached a level of approximately 3.9 sigma when combined with other datasets. This level of significance means that the chance of this signal being a mere statistical fluke is less than 1 in 10,000. To understand why this change is so significant, we can use the analogy of a car traveling down a long, straight highway. For decades, the standard model told us that the universe was on cruise control. The accelerator pedal was pressed down to a fixed position, and the car was accelerating at a constant, predictable rate. We could look at the speedometer and the odometer and calculate exactly where the car would be in an hour or a day. But the DESI data is like a high-precision black box recorder that reveals the driver has been moving the foot. The expansion is not on cruise control. Instead, the driver appears to have been pressing and releasing the accelerator over billions of years. This dark energy discovery changes everything about our trajectory. If the pedal is moving, we can no longer assume that the cruise control setting is the law of the road. We have to ask who or what is moving the foot. The phantom divide is like a physical wall on this cosmic highway. In the standard model, the value of -1 for dark energy is a hard limit. That value is the point where the energy is a perfect property of space. But the DESI results show the car drifting across that line and moving into the phantom regime, where the laws of physics, as we know them, begin to break down. This threshold crossing is far more than a mathematical curiosity. Is the universe entering a phantom phase? This phantom crossing is a sign that the very nature of dark energy may be more complex than a simple vacuum energy. We are seeing evidence of a dark sector that has the internal physics, the dynamics, and perhaps even the destiny of the sector that is separate from the matter we can see. The statistical weight of this discovery is creating a profound tension within the community. While some researchers argue that we need more data to reach the 5 sigma gold standard of a formal discovery, the consistency of the signal across multiple independent datasets makes the situation impossible to ignore. According to the comprehensive review by Eleonora Di Valentino in 2026, the preference for dynamical dark energy persists even if you remove any single dataset from the analysis. Whether you look at the galaxies, the afterglow of the Big Bang, or the distant supernovae, the universe is whispering the same message. The dark sector is not a constant. The standard model is failing because the model assumes a static reality in a universe that is fundamentally dynamic. The existential implication of this discovery is staggering. If dark energy is not a constant, the ultimate fate of the universe is no longer a simple matter of a slow, cold heat death. If dark energy continues to weaken, the expansion could eventually slow down or even reverse. On the other hand, if the phantom energy behavior is real, the expansion could accelerate so violently that the very fabric of space is torn apart in a big rip. By discovering that the cruise control is off, we have lost our certainty about the end of the story. The dark sector investigation has revealed that we no longer reside in a predictable machine, but in an evolving system whose final chapter is still being written by forces we are only just starting to name. But as the investigation shifts toward these changing ingredients, another contradiction has emerged from the dark sector, one that involves the lightest and most mysterious particles in the universe, the neutrinos. This mass discrepancy is known as the neutrino mass tension, and the tension marks the point where the physics of the largest scales in the cosmos clashes directly with the physics of the smallest particles in the laboratory. For decades, the standard model of particle physics assumed that neutrinos were massless. But the discovery of neutrino oscillations proved that these particles must have some mass, even if the weight is incredibly small. The context of this tension is found in the clash between the sky and the lab. In terrestrial laboratories, experiments like Katrin in Germany have been attempting to measure the mass of the neutrino by watching the radioactive decay of tritium. These experiments are looking for the tiny amount of energy that the neutrino carries away during the decay process. As of 2022, the Katrin experiment, using a massive silver spectrometer the size of a submarine, has set a hard upper limit on the mass of the neutrino at 0.8 electron volts. The spectrometer looks like a giant silver submarine, though one designed for navigating the quantum void rather than the North Atlantic. If you tried to take the vessel for a dive, you would probably just end up with the most expensive and least effective fishing boat in history. This massive electrostatic filter acts as a barrier, allowing only the most energetic particles to pass through the chamber. This Katrin value represents the maximum weight the particle can have based on direct local measurements. The Katrin spectrometer is more than a simple vessel. The instrument is a massive electrostatic filter that operates on the principle of magnetic adiabatic collimation. As the electrons from the tritium decay enter the main chamber, the electrons are guided by a powerful magnetic field that forces the particles to move along the field lines. The vacuum inside the silver submarine is one of the most extreme ever created on Earth, reaching pressures lower than the surface of the Moon to ensure that no stray air molecules interfere with the energy of the electrons. By applying a precisely controlled electric retarding potential, the researchers can filter out all but the highest energy electrons, the ones that carry the least amount of energy because the neutrino took the rest. This filtering process requires a stability of less than 1 part in a million, a level of control that makes the Katrin experiment a masterpiece of experimental physics. However, when we look at the universe as a whole, the cosmological data tells a very different story. By combining the Desi baryon acoustic oscillations with the Planck cosmic microwave background data, researchers have set a new upper limit on the total mass of the 3 types of neutrinos. This specific cosmological limit is approximately 0.064 electron volts at the 95% confidence level. This tiny value is nearly 10 times smaller than the limit from the laboratory, according to the research by Junxian Zhang and the Desai collaboration in 2024. This mass discrepancy represents a significant tension between the astronomical sky and the terrestrial lab. The universe appears to require neutrinos that are much lighter than our best laboratory experiments suggest those particles should be. The mechanics of this cosmological measurement are rooted in a process called free streaming. In the early universe, neutrinos were moving at nearly the speed of light. Because the particles are so light and interact so weakly, the neutrinos could easily escape the gravitational pull of the dark matter scaffolding. This neutrino movement creates a blurring effect on the cosmic web. If neutrinos are heavy, the neutrinos carry away more energy and suppress the growth of small-scale structures, making the modern universe look smoother and less clumped. By measuring the exact level of clumping in the galaxy surveys and the afterglow, cosmologists can work backward to calculate the mass of the neutrinos that must have been present to create that specific pattern. The central mechanical conflict is that the universe is so detailed and so well structured that this architecture leaves very little room for neutrino mass. If we accept the terrestrial laboratory requirements for the neutrino masses, we would expect to see a much smoother universe than the one we actually observe. To make the cosmological data fit the standard model, the neutrinos have to be so light that those particles almost do not exist at all. In fact, if you force the mathematical fit without constraints, the data often prefers a negative mass for the neutrino, a result that is physically impossible. This negative mass mirage is a clear signal that fundamental physics is wrong. This neutrino conflict is the scientific equivalent of a ghost on a scale. Imagine you are trying to weigh a phantom that you know is standing on a high-precision laboratory scale. The laboratory equipment is designed to detect the tiniest pressure, and the equipment tells you that the ghost must weigh at least 10 grams to even exist as a physical entity. You are confident in your laboratory. You have calibrated the scale 1,000 times, but then you go outside and look at how the ghost affects the environment. You watch how the ghost moves through a field of wheat, and you notice that the stalks barely bend at all. Based on the movement of the wheat, you calculate that the ghost cannot weigh more than 1 gram. If the ghost weighed 10 grams, the wheat would be crushed. You are left with the impossible choice. Is your laboratory scale wrong about the nature of the ghost? Or is your understanding of the wheat field incomplete? This mass situation is the scientific equivalent of your bathroom scale, telling you that you are 5 pounds lighter than you were this morning, while your mirror insists you definitely ate that entire pizza last night. The universe is telling us one thing, and our experiments are showing us another. In this cosmic mystery, the neutrinos are the ghosts. While laboratory experiments like Katrine set the 10-gram limit, the cosmological surveys act like a wheat field, providing a 1-gram limit. These two measurements are in direct conflict. We have a particle that appears to be 10 times lighter in the sky than the ghost is allowed to be in the lab. This astronomical discrepancy suggests that our understanding of how neutrinos interact with the dark sector is missing a crucial piece. Perhaps neutrinos are interacting with dark matter or dark energy in a way that masks their true mass on cosmic scales. The anomaly of the negative mass preference is particularly haunting for theorists. When the researchers at the University of Sheffield and other institutions analyzed the combined data from DESI and the cosmic microwave background, the most likely value for the total neutrino mass was negative 0.1 electron volts. This negative mass result is a mathematical cry for help. A negative mass has no meaning in our current understanding of physics. This impossible signal is the universe telling us that we are trying to solve a puzzle with the wrong pieces. By forcing the neutrinos to be the reason for the structure suppression, we are ignoring the possibility that the dark sector is the culprit. This neutrino tension is becoming a major wall for the Standard Model. According to a paper by Elbers and colleagues in 2025, this unphysical mass result is a mirage created by our assumption of a static dark energy. If we allow the dark energy to be dynamical, the neutrino mass tension starts to change. This dark energy connection reveals that the failures of the Standard Model are not isolated events. The expansion mystery, the growth tension, and the neutrino mass conflict are all connected through the dark sector. We cannot fix one without affecting the others. The ingredients of the universe are tangled together in a web of interactions that we are only beginning to unravel. The dark sector investigation has forced us to move beyond the simple, elegant lambda CDM model. We are now looking at a cosmos where dark energy is dynamic, where dark matter might interact with neutrinos, and where the very mass of the most common particles in the universe is in doubt. The pieces do not fit because we have been looking at the universe as a collection of separate static parts. We are realizing that the dark sector is a vibrant, active part of the cosmic architecture. As we stand at this threshold, we must prepare for the possibility that the Standard Model is profoundly incomplete. The model is a simplified map of a much more complex and interactive reality. The escalation of these failures brings us to the edge of a new paradigm. We have seen how the beginning of time disagrees with the present, how individual galaxies refuse to follow the rules of dark matter, and how the dark sector is shifting beneath our feet. The investigation has reached a point where we can no longer rely on the comfortable assumptions of the past century. The Standard Model is breaking, and in the cracks, we are finding the first hints of a universe that is far more strange and interconnected than we ever dared to imagine. We must now decide whether to cling to the Standard Model, or whether the dark sector is a dynamic, active system that refuses to be contained by our current mathematics. The investigation has revealed that the ingredients of reality are no longer static. The pieces do not quite fit, but here is the reality. The puzzle is starting to move, but where is the motion taking us? The motion detected in the dark sector is not an isolated event. As the investigation reaches the final threshold, the cumulative weight of the evidence demands a reckoning. For decades, the Standard Model of cosmology was treated as a complete set of blueprints for the universe. But, as the case has shown, the blueprints are failing at every scale. The motion Edwin Hubble first detected has accelerated into a systemic breakdown that threatens to collapse our entire map of existence. We are no longer looking at minor errors or statistical glitches. We are looking at a fundamental mismatch between our theories and the physical reality of the cosmos. The pieces do not fit, but here is the structural anomaly. The problem is not that we are missing a few details. The problem is that the very foundation of the model is unable to support the weight of the data we have collected. The investigation has reached a point where the individual anomalies have merged into a single, undeniable signal. We have traced the expansion rate mystery known as the Hubble Tension, the growth of structure failures in the SS tension, and the small-scale challenges within individual galaxies. Each of these failures was once treated as a separate mystery, a localized fire that could be contained with a minor tweak to the mathematics. But the fires have joined. The mosaic of failure is now complete, and the picture reveals a Standard Model that has reached the limits of the capacity of the model to describe the heavens. The discrepancy between the beginning of time and the present day is no longer a curious anomaly. The gap is a formal discovery of a broken architecture. To understand the magnitude of this moment, we must look at the history of the Lambda CDM framework. This model was born in the late 1990s, a decade of profound discovery that seemed to settle the great questions of the cosmos. In 1998, astronomers used Type 1a supernovae to discover that the expansion of the universe was accelerating. This supernova discovery was the birth of dark energy resurrected from a concept Albert Einstein had discarded decades earlier, the cosmological constant, represented by the Greek letter lambda. By combining this constant dark energy with the invisible scaffolding of cold dark matter, the Standard Model was born. For 25 years, this theoretical success was so complete that the consensus assumed the story of the universe was essentially finished. But the precision of the newest generation of tools has turned that success into a prison. The accuracy that once confirmed the Standard Model is now the tool that is tearing the model apart. The SHUROS team, led by Nobel laureate Adam Rees, used the Hubble Space Telescope to reach the 5 sigma wall in the expansion rate measurement. In the world of physics, 5 sigma is the threshold for a formal discovery, meaning the chance of the discrepancy being a fluke is less than 1 in 3.5 million. Simultaneously, the Planck satellite mission provided a map of the early universe with such high resolution that the predictions the mission made for the modern expansion rate are nearly impossible to ignore. When the 2 most precise measurements in history give 2 different answers for the same physical constant, the numerical discrepancy is no longer an error. The Standard Model is fundamentally broken. This structural realization is the scientific equivalent of a detective board covered in red string. Imagine a detective investigating a series of crimes across a city. At first, the crimes seem random: a robbery, a missing person, a strange signal from the docks. The detective treats each case as a separate file, but eventually, the detective steps back and looks at the map. The detective realizes that every witness described a person wearing the same unique coat. Every piece of evidence points to a single hidden actor moving through the city. This precipice is the moment where we stand today. The expansion tension, the growth anomaly, and the dark sector shifts are not random errors. These failures are the fingerprints of a single hidden truth that the Standard Model cannot see. The red string on our cosmic map connects the smallest particles to the largest structures, revealing that the entire architecture is governed by physics we have not yet named. The mechanical failure of the Standard Model is rooted in the assumption of simplicity. The model assumes that the dark sector is a static graveyard. Lambda, the dark energy, is treated as a simple number, a property of space that never changes. Dark matter is treated as a cold, invisible fluid that only interacts through gravity. This simplicity allowed us to calculate the history of the universe on a single sheet of paper. But the universe is not simple. The data from the Dark Energy Spectroscopic Instrument, or DESI, has shown that dark energy may be dynamic, changing the strength of the dark sector over billions of years. This dynamical discovery breaks the cosmological constant. If the value of dark energy moves, the foundation of the Lambda CDM model vanishes. We are realizing that we have been trying to describe a vibrant, interactive ecosystem using the language of a static machine. The evidence for this dynamical behavior is found in the expansion history of the cosmos. By mapping the baryon acoustic oscillations, the DESI collaboration has charted the history of space and time with a precision of better than 1%. When the researchers combined this data with the afterglow of the Big Bang and the light of distant supernovae, The expansion discovery changes everything. Specifically, the data suggests that dark energy may have been stronger in the past than dark energy is today. The standard model requires dark energy to be a constant property of space, but the universe appears to prefer a dynamic path. This preference reached a significance of nearly 4 sigma in the 2024 analysis, sending a shockwave through the community. The mechanics of this evolving energy suggest that we are approaching a threshold known as the phantom divide. If dark energy behaves as a theoretical substance that becomes more dense as the universe expands, the behavior is a direct contradiction of the cosmological constant. The data indicates that the universe may have already crossed this line, or is in the process of doing so now. This divide crossing is far more than a mathematical curiosity. The phantom crossing is a sign that the very nature of space and time is more complex than a simple vacuum energy. We are seeing evidence of a dark sector that has the internal physics and the destiny of the sector that is separate from the matter we can see. The standard model is failing because the model assumes a static reality in a universe that is fundamentally dynamic. The mass discrepancy provides another layer of mechanical conflict. In the laboratory, experiments have set a limit on the mass of the neutrino that is at least 10 times higher than the limit derived from the history of the universe. The cosmological data from Desi and Planck requires neutrinos to be so light that the particles almost do not exist at all. This negative mass result is a cry for help from the mathematics. A negative mass preference is a signal that the model is trying to account for a lack of structure in the universe by using the wrong tool. Structure is not missing because neutrinos are light. Structure is missing because the dark sector is more interactive than we assumed. We cannot solve the mystery of the smallest particles without also solving the mystery of the largest scales. The ingredients of reality are tangled together in a web of interactions that the standard model simply ignores. To understand why this entanglement is so dangerous, we have to look at the conjoined history problem. In modern cosmology, the universe is not a series of independent variables. The universe is a tightly woven web. When we attempt to solve the Hubble tension by adding a burst of energy to the early universe, a phenomenon known as early dark energy, we inevitably change the growth rate of structure. By making the early universe expand faster, we reduce the time available for gravity to clump matter together. This specific adjustment fixes the expansion rate but deepens the SA tension, making the universe look even smoother than the lensing surveys already suggest. This specific mathematical deadlock is a signal that our fundamental assumptions about the dark sector are missing a unifying principle. This scientific threshold is not the first time humanity has faced such a deadlock. In the year 1900, the physicist Lord Kelvin famously declared that only 2 small clouds remained on the horizon of physics: the negative result of the Michelson-Morley experiment and the failure of classical physics to explain blackbody radiation. These clouds were not minor details. The clouds were the symptoms of a complete failure of the classical paradigm. Within 2 decades, those 2 clouds had expanded into the storms of relativity and quantum mechanics, completely erasing the old maps of reality. Today, the Hubble tension and the ES8 growth tension are the 2 clouds on our cosmological horizon. These discrepancies are the signals that our current standard model is the 19th century map of a 21st century universe. The failure of the static assumption is like trying to predict the weather using a photograph. A photograph can tell you exactly where the clouds are at a single moment, but the image cannot tell you where the storm is going. To predict the weather, you need a movie. You need to see the motion and the dynamics of the system. For 25 years, the Standard Model has been a high-resolution photograph of the universe. But as our observations have become more precise, we have started to see the blur of motion in the edges of the frame. We have realized that the universe is not a static image. By assuming that dark energy is a constant, we have been trying to predict the future of a storm by looking at a single frozen moment in time. The investigation has revealed that the dark sector is a vibrant, active system that may involve interactions we have never considered. If dark matter can exchange energy with dark energy, the entire history of the expansion of the universe changes. This dark interaction could explain why the Hubble tension exists, resolving the discrepancy between the early universe and the present day without requiring us to throw away laboratory data. We are moving from a model of isolated parts to a model of an interactive system. The Standard Model is failing because the model treats the universe as a collection of separate files instead of a single, unified story. This paradigm shift brings us to the paradigm threshold. The Standard Model of cosmology has reached the limit of the capacity of the model to contain the reality we are observing. The 5 sigma wall is the boundary of our old understanding. Beyond that wall, a new physics is waiting. We are seeing the first hints of a universe that is far more strange and interconnected than the Standard Model allowed. The next step is not a minor revision, but a revolution that will change how we see the very fabric of space and time. The stakes are existential. If the Standard Model is failing, we are losing far more than a mathematical formula. We are losing our story of how we came to be. The case for the Standard Model of cosmology is closing. The verdict is a profound transformation of our understanding. The Standard Model remains a useful map for large-scale structure, but the model can no longer claim to be the final story. The gaps in our understanding are the windows into the next era of human knowledge. As we prepare for the final verdict, we must acknowledge that the truth likely lies between the math and the mystery. We must follow the data wherever the data leads, even if the data leads us out of the cage and into the unknown. The Standard Model is breaking, and for the first time in a generation, we are finally starting to see the universe for what the universe actually is. That motion has led us here, to the final room of the evidence locker. For nearly a generation, the Standard Model of cosmology acted as a secure cage for the history of the heavens. Scientists walked into this cage with a single set of keys and expected every lock to turn. For a long time, the keys worked. The Lambda CDM framework described the faint glow of the Big Bang and the rotation of galaxies with a precision that seemed to signal the end of the mystery. But as the investigation has shown, the cage is no longer secure. The locks are jamming, the doors are hanging off the hinges. We have reached a point where the very architecture of the cage is warping under the weight of new data. The investigation must now conclude by looking at the cumulative evidence to determine the final verdict. The primary failure is the Hubble tension, a conflict that has moved from a minor statistical annoyance to a full-blown crisis. In 2021, Nobel laureate Adam Riess and the Shajaroz team reached the 5 sigma wall, the gold standard of scientific proof. Riess used local observations to calculate an expansion rate of 73.2 kilometers per second per megaparsec. However, the Planck mission, observing the early universe, predicted a rate of only 67.3. The discrepancy is not a small gap. Instead, the discrepancy is a fundamental disagreement between the beginning of time and the present day. The mechanics of this mismatch are rooted in the physics of the sound horizon. In the early universe, sound waves traveled through the hot plasma before being frozen into the distribution of matter. Scientists use the size of these frozen waves to calculate the expansion history. The Hubble tension reveals that our measurement of the sound horizon in the early universe does not match the expansion we see in our modern neighborhood. The gears of the cosmic clock are no longer synchronized. Imagine a detective investigating a bank robbery. The detective looks at security footage from the morning and sees one person entering, but the afternoon footage shows a completely different individual leaving. The standard model insists these are the same person who simply changed clothes, but the detective can see the fingerprints and height are different. The identity of the individual has fundamentally changed. This identity gap represents the reality of the Hubble tension. The early and late universe are behaving like two different entities that happen to share the same name. We are trying to force a single identity onto a cosmos that has clearly evolved beyond our current definitions. The failure extends to the growth of structure known as the ESA tension. Observations from weak lensing surveys show that the modern universe is smoother than the standard model predicts. Matter is not clumping together as quickly as the early universe data suggests the clumping should. This structural growth failure is a signal that gravity, or the dark sector, is behaving unexpectedly. The investigation also uncovered small-scale challenges within individual galaxies, such as the cusp core problem. While the standard model predicts dense, dark matter peaks at galactic centers, dwarf galaxies exhibit quiet, hollowed-out cores. The data shows a universe that is stubbornly refusing to follow the instructions of the standard model. This systemic breakdown leads to the first major finding. The standard model is no longer internally consistent. A model is only as strong as the ability of the model to explain all the data simultaneously. For 25 years, Lambda CDM was celebrated for the simplicity of the model, but that simplicity has become a liability. To fix the Hubble tension, researchers must add new ingredients like early dark energy, which often makes the ESA tension worse. Fixing one part of the sky causes another part to break. This mathematical deadlock is a clear sign that the model is missing a fundamental unifying principle. The history of this success was built on three pillars: inflation, cold, dark matter, and a cosmological constant. For a long time, these pillars were strong enough to support our observations, but each is now showing signs of structural failure. Inflation is a theory without a confirmed particle. Cold, dark matter has never been detected in a laboratory, and the cosmological constant, represented by the letter lambda, is a number that is 120 orders of magnitude smaller than the value predicted by quantum physics. We have been living in a house built on pillars that we cannot see or fully explain. The current tensions are the sound of these invisible pillars beginning to crack. The mechanical nature of these cracks is most evident in the behavior of dark matter. In the standard model, dark matter is assumed to be cold and collisionless. This allows the model to predict large-scale structures with incredible accuracy. But at the scale of a single galaxy, the assumption fails. If dark matter were truly collisionless, galactic centers would be incredibly dense. The fact that galaxies have flat cores suggests that dark matter might be interacting with other dark matter or ordinary matter in ways the standard model forbids. The mystery of the small-scale challenges is a direct challenge to the cold and collisionless definitions of the standard model. Consider the analogy of a master mapmaker. The mapmaker creates a beautiful map of the entire world that looks perfect from a distance. But when a traveler tries to navigate a specific city, the traveler finds that the streets are in the wrong places. The map maker insists the map is correct and the city is wrong. This inaccurate map represents the stance of the cosmological consensus. The Standard Model is a great map for the ocean, but a terrible map for the streets where we actually reside. The failure at the local level is a sign that the entire method of map-making needs to be revised. The acknowledgement of this inconsistency is the first step toward a new understanding. We are finding that the universe is far more complex and interactive than our simple formulas allowed. We are losing the comfort of a settled story, but we are gaining the opportunity to discover a deeper truth about the nature of reality. The investigation now turns to the paradox of the dual universe. The Standard Model appears to work for parts of the sky, but fails for the whole sky. This paradox is most visible in the data from the Planck satellite and the Dark Energy Spectroscopic Instrument, or DESI. Planck provides a high-resolution map of the early universe, while local projects provide direct evidence of the modern universe. Both sets of data are statistically robust, but they cannot be connected by the current Standard Model. The mechanics of this paradox are deeply tied to the lensing anomaly in the cosmic microwave background. The Planck data shows an excess of gravitational lensing, suggesting the universe might be closed with a positive spatial curvature. This CMB finding is a direct contradiction of the flat universe assumption core to lambda CDM if the universe is closed. The entire history of cosmic expansion changes. The lensing anomaly is a ghost in the machine, a signal that the shape of the cosmos might be different than the shape we have been assuming for 30 years. Imagine a detective who finds matching fingerprints at a crime scene, only to discover they belong to two different people residing on opposite sides of the planet. This data conflict represents the paradox of the dual universe. We have two sets of data that are both perfect, but they point to different versions of reality. One expands slowly with smooth matter, the other expands rapidly with dense, local structures. The Standard Model is the detective trying to explain how one person can have two different sets of fingerprints. The only way to solve the paradox is to realize the person is not who we thought they were. The tension is further complicated by the neutrino mass tension. Particle physics experiments show that neutrinos must have a minimum mass. Yet cosmological data requires neutrinos to be so light they almost do not exist. The universe is telling us that neutrinos are lighter than the laws of physics allow. This neutrino conflict is a cry for help from the mathematics. The model is trying to account for a lack of structure in the cosmic web by pushing the mass of neutrinos to an unphysical limit. The smallest particles and the largest scales are locked in a contradiction that the Standard Model cannot resolve. Our definition of the whole universe is incomplete. We assumed the dark sector was a static, unchanging background, but the paradox suggests the dark sector is a dynamic, interactive system. If dark energy changes over time, or if dark matter interacts with other species, the connection between the early and late universe is restored. The failure of the Standard Model is a sign that we have been looking at a movie through a single, frozen frame. The true dynamics of the cosmos are finally beginning to emerge from the shadows. What comes after the Standard Model, every great model, eventually reaches a limit. In 1900, classical physics seemed complete except for two small clouds on the horizon, which became relativity and quantum mechanics. Today, the Hubble and S8 tensions are the two clouds on our cosmological horizon. We are standing at the threshold of a paradigm shift. The next step is a revolution in our understanding of the dark sector and the nature of space as an entity. The mechanics of this new physics are appearing in the latest data. The 2024 results from DESI revealed a preference for dynamical dark energy. This means dark energy may not be constant, but a substance that evolves. The data suggests dark energy might cross the phantom divide, becoming more or less dense as the universe expands. If dark energy is dynamic, the foundation of the standard model vanishes. The new physics will likely involve an interactive dark sector where dark matter and dark energy exchange energy and influence the growth of structure. The search for this new physics is like standing on the shore of a vast ocean. For a long time, we thought the shore was the entire world. But now the tide is coming in, washing away our old maps. We can see hints of a vast ocean beyond the horizon, filled with phantom energy and interacting dark species. The failure of the standard model is an invitation to sail into the unknown. The ocean is terrifying, but the deep is also where the true history of the universe is written. This paradigm transition requires a state of epistemic humility. For 30 years, we operated under the assumption that the mystery was solved. But the failures we have uncovered, the 5 sigma wall, the growth tension, and the small-scale crisis, are reminders that nature is far more creative than our consensus allows. To acknowledge that our best model is broken is the highest form of scientific integrity. We are clearing away false certainty to make room for the actual truth. We want to invite you to join this search. The questions we are asking are some of the most profound in human history. How did the universe begin? Why does the cosmos look this way? And where is the cosmos going? The answers are in the data currently being collected by telescopes around the world. This cosmological investigation represents a journey that requires intellectual honesty and a willingness to follow the evidence, even when the evidence leads away from the comfort of the consensus. We may not have a new standard model yet, but we have a significant alternative, a genuine mystery that is waiting to be solved. The final verdict is that the standard model of cosmology is a broken masterpiece. The model was a triumph of human reason, but the universe is bigger than our models. The tensions and anomalies we have investigated are the fingerprints of a reality more interactive and dynamic than we imagined. The truth likely lies in the gap between the math and the mystery. We must continue to look into that gap, to measure the expansion, and to track the growth of the cosmic web. The standard model is failing, and in the cracks, a new universe is finally coming into view. Keep asking questions. The pieces may not fit yet, but this discrepancy is exactly why we must keep looking. So here is what we know. The standard model of cosmology is failing across multiple scales, but this cosmological discovery really means that our entire map of existence remains a work in progress. Every time we think we have figured out the universe, the cosmos turns around and shows us we are just scratching the surface. This channel is a labor of love, but the work also takes a lot of late nights. If you want to buy me a coffee or just help keep the lights on, check out the donation link below. I am incredibly grateful for everyone who has supported the channel so far. But mostly, I want to know what you think. What do you think is causing the cracks in the dark sector? Let me know in the comments. I go through all of the comments. I will catch you in the next one. Let curiosity guide you. Keep learning and know that you are always appreciated.